So let me just take this time to welcome everyone to this Radio Shop chat organized by the SpectrumX, which is an NSF Spectrum Innovation Center. My name is Scott Barker. I'm a professor of electrical and computer engineering at the University of Virginia and the deputy director of the Broadening Participation Working Group for SpectrumX. Before we begin, I'd like to share a couple reminders with everyone. If we go to the next slide. First, I'd just like to remind everyone that SpectrumX is the world's largest academic hub, through which all stakeholders can collaborate, innovate, and make the best use of this radio spectrum that is so precious for the benefit of society. SpectrumX has over 150 researchers, 30 member institutions, and we're always looking for adding additional researchers and institutions to our family. It's a large organization, as you can see, spread over the US. It's been funded primarily through a 5-year award from NSF, and we have continued to partner with additional government agencies and institutions to sustain that effort. If we go to the next slide. So this just shows a little bit of the ecosystem in which SpectrumX as an organization is situated. You can see a lot of acronyms in here, but a lot of these are various government organizations. You'll see many that are familiar: the FCC, NASA, NOAA, NSF, DARPA, as well as industry organizations such as the NextG Alliance and Wind Forum, 3GPP, and the IEEE Standards Association. And then there's international organizations as well, such as the WRC and the ITU-R. Next slide, please. So before we jump into our talk, just want to remind everyone that the purpose of the Radio Shop Chat series is really to bring together the community to educate, debate, and inspire next steps in our collaborative research, our workforce development, and policy outreach. And then finally, these Radio Shop chats follow what we call the Chatham House rules, which means that participants are welcome and free to use the information received, but please do not identify the affiliation of the speakers nor any other participant that may be revealed during this session. So take the information that is shared and use it, but please don't attribute that without permission. And next slide, please. So thank you again for your participation. These are just some QR codes for additional information to share information with us if you'd like to get involved. To find out more about the SpectrumX Center, follow us on LinkedIn or check out the website. So at this point, I'd like to introduce our speaker for today and the topic. It's my great pleasure and privilege to introduce Dr. Rashaunda Henderson, who's going to be talking to us about performance of antenna in package designs at millimeter wave frequencies. Dr. Henderson is a professor in the Electrical and Computer Engineering Department at UT Dallas in Richardson, Texas. She received her undergraduate degree from Tuskegee University and then graduate degrees from the University of Michigan, where both she and I attended at the same time. So we were lab mates, and we go way back and have a lot of friends that we get together with and see every year. So that's great fun. Dr. Henderson joined Motorola Semiconductor after grad school, where she worked on a number of different projects in microwave and mixed signal technology until 2007, when she joined UT Dallas and co-founded the High Frequency Circuits and Systems Laboratory, which focuses on millimeter wave design and development of circuits, integrated packages, and antennas for wireless communications. She's published a number of over 100 different journal and conference papers in this area. She's a senior member of the IEEE, and she has served in 2022 as the president of the IEEE Microwave Theory and Technology Society, which was a tremendous, tremendous service that she provided to our society and the IEEE. Dr. Henderson is really passionate about education and teaching the next generation of students and encouraging them to seek careers in science, technology, engineering, and math. So without further ado, Rashaunda, thank you very much for being here talking to us today, and we're looking forward to your talk.
Thank you, Scott. How does it sound? Everything sounds okay?
Good on my end.
Okay. All right. Let's see. Do you see the talk and not my desktop? You just see the talk, right?
Yep.
Okay, because my desktop is a mess. But uh, thank you so much for the invitation to present. I'm very happy to put it in full screen mode to be here. Let's see. So let's see. Okay. So I want to get started with a few things and just sort of resonating with what you said about the Spectrum X. I'm so excited to be able to present this venue in the form of people that's part of your ecosystem is very exciting. And so I know that we're all aware of how congested the spectrum is and how important it is to coexist. And so, I just kick off this slide to talk to you about where I am actually today. I'm at a meeting for another group, which is called Smart Hub. And Smart Hub actually was competing for that same money that Spectrum X received. I think that was, I don't remember if it was 22, 23, but because they didn't win that award, they continued to remain together, those researchers. And so they have been funded in some part to cover topics very similar to what you all are looking at. And so they have 25 researchers over 15 universities, and I'm part of that center in the area of workforce development. So I'm currently at something called Spectrum Sizzle. And so what that is a workshop for undergraduate students. And today we're in I guess the last day of what we call an advanced sizzle. And so we talk to students about spectrum policy, passive circuits and systems, communication systems, wireless circuits, reconfigurable circuits. And so this work, specifically on the workforce development piece, has been funded by the National Science Foundation. So, we're resonating more than we know actually this today and this week. So now I want to talk about the research that I'll cover in this presentation. And so while I'm part of Smart Hub, I am not my research is not applicable specifically to the issues associated with the congested spectrum. I'm more of a user, I would say. And so we've been funded by the Semiconductor Research Corporation in the past to look at ways that we can actually develop low-cost solutions, in particular from millimeter wave antennas. And so we entitled that Millimeter Wave Packaging Research, and in particular, it's called Antenna and Package. So the contributors and the collaborators that we've worked with are from UT Dallas, and within UT Dallas, we have a Texas Analog Center of Excellence. So that's a center that's been in place, I think, now more than 14, 15 years. And then we have a lot of collaboration with Texas Instruments. And so the work that I'll be presenting today and the faces that you see on these pictures are those students and or professors who've collaborated on this work. And then there's some names on the right-hand side. These are, second, let me see. I get trying to get the laser pointer. Okay. These are students that have graduated and gone on, and even these students have graduated since then. So just a quick sort of brief about the importance of what we're doing is if we think about system on a chip, packaging, and then system in packaging technologies, there are really a lot of opportunities. Quite honestly, I think when we think about semiconductor manufacturing, we know about Moore's Law and how technology has continued to develop. Now, I know there's some limitations as the nodes get smaller, but there's a systematic way in which circuits, chips are manufactured, whereas on the packaging side, it's a little bit more ad hoc. And so there's really a need to develop some systematic techniques and ways, especially as we push the operating frequency to realize solutions that are going to be cost competitive. And also, I think we want to bring some of those solutions here to the United States. A lot of the packaging work that gets done and is happening overseas. And so there's a big effort to do those things. And so in this slide, we're really just trying to highlight just the challenges that exist. So you have materials and process challenges as relates to the properties of the materials that are going to be used in packaging, the mechanical properties, thermal coefficient of expansion as you put multiple materials together, how will that affect the performance of your circuits, thermal challenges as it relates to heat transfer, electrical challenges, that we're highlighting here as it relates to interconnects and transitions as you take maybe a silicon chip and you want to place it in an encapsulated structure. How does that impact performance, and how do you make sure that whether it's a low voltage or high voltage solution that you're going to have a good result. And then as you start to thin your chips and really assemble things, are you going to make sure they survive actually? So just like I think what's going on in the spectrum field, packaging is a multidisciplinary area. And so we need electrical engineers, we need physicists, mechanical engineers, packaging research folk, as well as those who are interested in antenna design. And so it just takes all kinds to really put together a great solution that's going to meet demands that exist. And so I guess I want to say that I can't see if there's a hand up, or if Scott, feel free to stop me if there is a question. So I don't mind stopping in the middle of the talk. Okay.
Sure thing.
Okay. And in particular, when it relates to packaging, as I mentioned, there's a lot of solutions, and we're trying to focus on the quad, flat, no lead package, our QFN. And so those are typically used to physically and electrically connect ICs to printed circuit boards. And they're lead frame based chip scale packages with pads instead of pins. And they're quad because they have four sides, flat because a flat pack surface mount component. And then they don't have leads. So you normally would use epoxy molding compounds for these QFNs because they have low stress, low moisture absorption, high adhesion, low viscosity. And then we ultimately want to produce things that are low cost and have good electrical and thermal performance. So now I'm going to focus on two separate papers that were presented in 2024. And the first one is really talking about the packaging aspect of this work. And then the second one is going to talk about the antennas that we have designed and characterize those antennas in a package configuration as well as outside of a package configuration. Because as you go to these high frequencies, the way to take measurements becomes a challenge. So this outline just shows that we'll talk about just some core and coreless packages, the material characterization techniques and measurement results from that, and then a quick conclusion and references, and then we'll go into the next paper. So why millimeter wave? And of course, talking to this community, you all already know this, but in particular, we're curious and we'll want to take advantage of the small footprint, the high angular resolution that could be achieved. And we all know that we can get higher data rates because as the bandwidth or the frequency increases, the percentage bandwidth is the same, but you get higher frequency, and so that gives you a benefit. And we have higher transmission rate, and then we have the availability of these unlicensed bands. So current applications are from 24 gigahertz all the way up to 140 gigahertz, for example, ranging from automotive radar, metrology, wireless communication, and imaging and security. And then prospective applications include drones at 90 gigahertz to 110, autonomous vehicles up to 200 gigahertz, and artificial and virtual reality. But how does this work? So what you have oftentimes is your RF integrated circuits and front-end modules, and then you have your antenna. And so where do you place it? Do you place it on the chip or do you place it in the package? And then how do you connect everything together? And so we were tasked at the time to look at antenna and package, and in particular at very high frequencies. And so when we're talking about antenna and package, we're really trying to take advantage of substrates that normally would be interfaced with the printed circuit board, and placing those antennas in that area so that we can really utilize the silicon die for what its purpose is. And quite honestly, sometimes the silicon die, because the dielectric constant is so high, it doesn't necessarily produce efficient antennas. So, but the silicon die is useful in that you can produce active circuits, analog, RF, digital, and power. But you also need to be able to take advantage of a multi-layer substrate, which is what we're proposing for the package, which can host transmission lines for interconnects, antennas to radiate ground planes, reflectors. And then we also, if we need to, we'd like to be able to embed passives. And then we assemble all of that together in a printed circuit board. And so from the design requirements perspective, we want our silicon die to be matured so that it can operate at high frequencies. Oftentimes, and being part of this Texas Analog Center of Excellence, we focus on silicon RF, if you will, or RF CMOS. So we want to try to do low cost fabrication of transceivers. And so we're trying to push the limit of what silicon can do. And we know that there are other technologies that give you higher power, but the effort has been always to sort of focus on using silicon techniques. And if you have that chip and you can get a certain amount of performance, you ultimately need to package it. And so it's going to be on a substrate and encapsulated. And so you have to start to take into consideration when you start looking at these packages that are not, they're sort of lending themselves to traditional printed circuit board. They're going to have surface roughness issues, material properties issues that may, in general, inhibit its performance for higher frequencies. And then ultimately, we need to characterize those packages. So let me just get my phone to make sure I'm not over time. So we talk about in this slide core and coreless packages. And so what I'm showing on the left is some work out of the Texas Instruments from one of our classmates in Michigan on what we call flip chip scale packages. Okay, and so what this includes is the die shown here at the bottom. We have these ball grid array, just the balls, so that you can attach this package to a larger printed circuit board, but there's a core. So an FR4, for example, some type of core, but you also see that there's vias, plated through hole vias, micro vias, where you can have a larger substrate, and potentially you can add an antenna here, but there's definitely an opportunity to do multi-layer organic type of research. And typically when you use these types of materials, as you see here in this lower left, you have this glass fiber, I should say weave pattern, which defines the dielectric property of the core, and oftentimes it's susceptible to process variation. So very different from silicon, for example, or gallium arsenide. And so you have to make sure you understand the glass fiber and weave. And for example, we know that a lot of times Rogers 5880 is a very good dielectric material, but it's very expensive. And so people have started looking at some lesser performing materials, but they have a better cost model. And so here we're showing an example of a flip chip enhanced QFN, sort of a model that we're proposing. And so here on the right-hand side, there are multiple layers so that you can, if needed, include vias and process transmission lines. You have what we call this area is the encapsulation area, metal layers 1 and 2, and then another interface layer, which is metal. And so we have, in this case, 2 different dielectrics. Now, if you look here at the bottom right, what you're seeing is the cross section of this stack. So we've taken the package, for example, and sliced it. And so what you're seeing here is the copper and different walls of this is the dielectric and then the metal layers. And so you see that they're sort of irregular as it relates to maybe if you've looked at a chip, an IC, and you've taken a slice of that, has very nicely defined walls. But in this case, we're still seeing things that are not as I'll say beautiful. But the particle size in this particular material is called Ajinomoto Build-up Film. It's relatively small and is relatively evenly distributed, making their designs robust from a dielectric permittivity and a dielectric loss variation perspective. So one of the things that's extremely important, and I think we all know this, is when you start designing circuits, whether they're interconnects or antennas, is how do you measure the material properties. And so this is just a slide kind of showing us what what the application space would be, and then the operating frequency in which my group and another group we've collaborated with has used different techniques to look at substrate and mold compound properties so that we can accurately determine their performance or their material properties for performance sake. And in particular, we received some materials from Texas Instruments, and they gave us material that was about 700 microns thick. And so we had to work within the constraints that they provided for us. Now, there's a lot of people doing material characterization in the world, and so there are higher, I would say, techniques that are really accurate. A lot of the resonator techniques, but they can be costly. And so we were working on trying to do some lower cost techniques that could give us some information about that material, because they would not tell us what the material specifically was because they had it was proprietary. So this is an example of us using a known material, the Rogers 5880 that I mentioned before. And so we did some characterization of that material from very low frequencies all the way up to 110 gigahertz. And we used 3 different techniques. And so one is this is an air line, so it's a transmission line, which is very short, but the center conductor is metallic and you have an outer conductor, but the dielectric is air. And so we can insert small donut-shaped pieces of the dielectric material in there and use that to characterize the material. And we can do that up to 67 gigahertz. We could take a rectangular waveguide structure, and this is just the holder. And so the waveguide or the material sits in there. It's normally air in there, and we can fill the material and then we can characterize the waveguide based data. And so that is from 75 to 110 gigahertz. And then Some of the material, as I mentioned, they gave us, it was in fixed sizes, which we couldn't easily machine into the shapes that we wanted. So then we actually built ring resonators on top of the dielectric material, put metallic copper tape on the back side, and then would add connectors and take measurements. And so that's where we're getting some of the low frequency results. And so once again, we use this Rogers material because we know that it's consistent. And so we were able to show some of our results compared to that of the data sheet. And so we get reasonably very good dielectric constant, but the loss tangent with these techniques is not the best because this is a really low loss material. So this is just some information about the different techniques and what you can, the pros and cons of them. And so for the work that I'll be sharing over the next few minutes, we are really trying to look at and design antennas from 140 to 220 gigahertz. And so we're going to use a free space technique. And so what we're showing here is that we use a network analyzer, and the network analyzer is used even in these measurements. And we measure the scattering parameters, and then we do some we apply an algorithm. And in this particular case, because we're doing this at WR5, we place the extenders, and this is really sort of a cross section of what you're looking at. We have one sort of at a raised height. We have another one at a lower position. And so we're using horn antennas to send out the signal, and the signal will go up and or down. And then we have these parabolic mirrors to sort of guide the signal so that we can get essentially a two-port measurement. Okay, so what we're going to use is the Nicholson-Ross-Weir equation for a finite thickness sample suspended in free space. Okay, and so that ABF material is usually available in thin sheets varying from 50 to 100 microns. And so with such a thin sample, with this method that I'm talking about, it's difficult to get an accurate measurement. So one of the things that we did is started to try to make it a thicker material. So this is a picture, once again, trying to show you the real structure, our setup. So this is one of the extenders. This is the second one. So you see that height difference. And so we also put it in a glass chamber because we did some measurements at a higher temperature as well. And so we wanted to protect the micro extenders, sorry, the frequency extenders from the high temperature lamps that were used. And so this is a parabolic mirror and the horn antennas. And so the sample was placed here in the sample holder. So using the algorithm, what we're saying here is this 100 micron thick sample shows considerable variations over frequency. And so that was what led us to realize, okay, we needed to go with a thicker material in order to make sure we accurately characterize the properties. So this is showing results from 140 to 220 gigahertz. And so then my student worked on a sample preparation. So he wanted to take one piece. So let's say that's 100 microns or 70 or 50 microns. And then he puts together a total of 5. And so therefore he's stacking them and he's trying to make sure that there's no air gaps, as he's showing here, no contaminants in the sample preparation. And so he does some hot rolling to ultimately produce what we believe is more of a single material. So these are just some images that show, so this says material A before, and then material A after it's been hot rolled. And so what he singulated out a piece. And so that's what you have. And so he sends a bubble formation on the edge and rolling marks are visible. And so this is the second material B. So because of these marks, we wanted to make sure we singulated outside of that area. And so this material is about 600 microns thick. Okay, so then after using the thicker material, we are able to see for sure on the dielectric constant or the decay side that we're getting a much flatter response compared to what we had seen in the previous slide. Now the loss tangent is still um, it's still variable, but it's still an improvement across the frequency. And so we, like I said, we sort of zoom in on accuracy on the dielectric constant side because this technique is not as favorable for loss tangent. And so from the manufacturer, Ajinomoto, they also did measurements and they shared them with us, and they did them from 220 to 325. And the student that worked on the original characterization of this material, he also has data in this frequency range as well, but on a thinner sample. So, but what they can show is that 50 micron thick material, they're getting a dielectric constant about 3.3. We're getting 3.33. And then their loss tangent you see is 0.0067. And then when they went a little thicker, their loss tangent increased to about 0.01. And so, we have a variation with respect to that. But we are getting close when it comes to the dielectric constant. And after we measured the material, we 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 took the material and then used it to build what we call a test vehicle. And so a test vehicle, in the next part of the presentation, I'll talk about the antennas. We put transmission lines because we wanted to use those to verify the performance. We could design the interconnects and then compare simulation to measurement. And so this is the test vehicle, top side and bottom side. This is a copper that you're seeing, sort of that light orange color. And then the back side here is when we actually um, take this package and then put it on a larger board, we need to do some soldering. And so that's sort of what you're seeing here. Just some lines to help us do that. So we probe not the antennas, I'm sorry, but the transmission lines. And so here's just an image of what that looks like. And so this is to your bottom left, the comparison of the return loss. And so um, we are not, the insertion loss is somewhat reasonable, but the electrical length between these two, the measurement and the simulation is a bit off. However, and so I'm sorry, that was with the 1x. So that was the thin sample. But when we made the thicker sample, which was 5x of the original size, then we were able to get much better agreement between the simulation and the measurement from very 100 megahertz all the way up to 220 gigahertz. And so we are showing three different banded measurements. So we have our VNA works up to 110 gigahertz. Then we use WR8 modules from VDI, and then we use WR5 modules. So the summary about this work is that we're able to show suitable characteristics due to smaller particle size using this ABF material, and we have good correlation for the dielectric constant, and it agrees reasonably well with the work of the manufacturers. Okay, so these are the references. And now I want to go into the other paper, which is really talking about the antennas, because if you have the dielectric material properties, then you really can go into the design of the antenna and build them really around the flip chip package. So really the impetus and the motivation behind this is driven by, I'll show just this image here where Texas Instruments fabricated a radar, and in the original design they built their antennas on the board, and so you see size 55 millimeters on a side, but then if they really can integrate the antennas and the transceiver, they can reduce that size. So when you build those antennas into the package, then you can end up with a smaller solution. And so that was the motivation. And then the pictures that you're seeing are just different solutions that exist in literature. And once again, they're sort of all over the board, and they all have pros and cons associated with them. And this slide just really talks about some of those solutions that exist in manufacturing. Texas Instruments and Infineon, they have worked on solutions where they've built antennas in the package. And so we're looking at going beyond 90 gigahertz. And we're in particular looking at a slot bow tie antenna in this presentation. So in terms of characterizing these antennas, some of the techniques that exist um, at low frequency, people can use probes to take measurements, but we really want to move away from a probe solution. So that's one shown here where you have an antenna and you have a ground signal ground probe, because there could be potentially radiation from the probe. And so you may not really be picking up the true performance of the antenna when you ultimately want to get the radiation pattern. People have also used in launches, and so this is one that's fairly customized, and it can go all the way up to, I think, 110 gigahertz by Southwest Microwave. And so in the literature, we had found that someone else had really built what they're calling sort of like an in-launch or a direct waveguide feed. And so they've placed, this is a rectangular waveguide, and this is a transceiver. And so there's other components here for power. But this is where you have your the signal, and you have an antenna that you're, or I'm sorry, automotive radar that you're trying to ultimately feed. So they have what I would call a whole solution with a chip. The work that I'll be presenting, we don't have an IC associated with it. We just have the antenna. So in this particular case, kind of going back to what I was talking about earlier about this flip chip EQFN package, we are going to place our antenna on the top layer. So we have two metals, two dielectrics, and then we use something that we call walls. And so these walls, based on the process, we can actually stack vias or place them around each other, and they look like virtual walls as opposed to not. So that's why we define them as walls. Okay, so what you see is the antenna. This is just a bow tie antenna. It's fed with coplanar waveguide, and it can give a fairly broadband performance. And then we have to simulate and design with these walls in place so that we try to capture everything that's taking place. And then we add an overmold material, because ultimately we're going to cover the antenna. And so these are the material properties of those, the materials that are being used. And so when we originally do design in HFSS, we do what we call a standalone bow tie antenna, where there's no package around it. We just feed it here, but we do have that overmold on top so that it's a dielectrically covered antenna. And so we expect a simple radiation pattern, and so that's what we see. And we're looking at this from 150 to 210 gigahertz. Excuse me, and we're just looking at the S11, or the return loss over the frequency, and we have a good minus 10 dB match across that band. And then after you build it as a standalone, we start to process through building it into this test vehicle that I made mention of before. So we extend the length of the coplanar waveguide feed in this image number 2. Then we place it in the environment where it's ultimately going to sit on a larger printed circuit board. And so that's on the order of 12 millimeters on the side. And that's originally by itself. But then, because we were trying to test multiple antennas or multiple configurations of measurement of the antenna, we simulated once again with the interconnects in place, and then these different variations on the antenna design. And then we finally simulated on a larger 40 millimeter on a sideboard, because that's what we need to actually ultimately put it together for our testing. Okay. So here is just the slide is just sort of once again talking about what the test vehicle contains. So it has 4 main antennas. We have 2 slot bow tie antennas for ground signal ground probing. And then we have 2 for this, I'll show in a minute, called backside feed using a waveguide. Because we know we can probe it with ground signal ground probes, but we think that's going to inhibit the radiation pattern. And so we really want to try to design a feed from the backside, similar to that radar work that we had found in the literature. And so this is really a stack up of the vias and the transitions that get us from feeding it from the bottom to feeding the antenna in and of itself. So these are just those layers. And so that's completely simulated as well in HFSS. And so after we build it, so what you're seeing here, this is the antenna, and it's sitting on a larger board, this 40 millimeter on a sideboard. And we've taken the original, what we call the EQFN package, which was manufactured by a company in Taiwan. And then we've brought it back, and it's actually this element here. We've flipped it, and Texas Instruments has helped us by actually placing bumps on it, that whole capability of soldering it, and put it together for us. And so this is a rectangular waveguide, and the transitions that I talked about here are utilized in order to feed the antenna, and they help us with the alignment of this so that it all works correctly. And so we've built some pucks to actually place the waveguide on there accurately and make sure everything is aligned. And so that's really what's we're trying to and show in this picture. And then the other way in which we take measurements of the antennas is just using a traditional probe. So here's a probe station, and then we zoom in. So we have our probe, and we're trying to feed the antenna and take a measurement there. So that will give us the S11 of the antenna, the return loss. But then if we really want to get the radiation pattern, we can use this technique, this backside waveguide feed, or we can use the ground signal ground probe again in a spherical chamber. And so what we will show in the next few slides is characterization of the antenna for both feeding approaches. And we're looking at the bandwidth of the minus 10 dB return loss. And then we're going to look at a couple of the radiation patterns. So originally, we have our simulation that's considering all aspects of this antenna. That's one of these antenna in this 40 millimeter on a side environment. And so that's what you see here in this simulation. Now we are shifted off from the measurement. And so my student believes it's a height mismatch, but simulation is supposed to give us 13.5 gigahertz bandwidth, and what we measured was more like 18.4. And so we believe also that our transition that was designed was not optimized. And so the performance bandwidth in general is limited. So he thinks it's a shift due to this dimension mismatch and coupling of the patch of the transition. So there's a patch. I didn't speak too much to it, but there's a patch that helps us couple the waveguide signal up through to feed the antenna. And then when we take a measurement of the antenna, really with our ground signal ground probes, because it's supposed to be a dielectrically covered antenna, this is what it looks like. We literally take the we receive the antenna from the manufacturer, and you see the copper, but then when we send it to Texas Instruments, they encapsulate it, and then we ask them to remove the dielectric so that we could probe it. So they did a laser etch of the dielectrics, but they're still covering really where the radiation of the antenna would be radiating here, but this is just the feed that we can see. And so you're seeing the S11 measurement using a ground signal ground probe. And so simulation is at 48.8 gigahertz, and 51.2 is what we measured, that 10 dB bandwidth. Now we know that the bandwidth of the antenna, things have changed, say, from the original standalone antenna, and every step in which we increase the size of this structure or add things around the antenna, the performance has changed. So the original antenna is somewhat different from this final one that we're getting to, not to mention that now we've created this sort of heterogeneous environment where we've opened up the dielectric so that we can actually probe the antenna. So that's changing performance as well. But the only way that we can measure that antenna is any other way is to measure it from the bottom side through the waveguide. Now, for the S11, but we also want to get the far field radiation pattern of the antenna. And so we have a system by NSI, MI Technologies. And so it's a spherical chamber. And so we place our waveguide extender on this antenna arm, and then we can place our antenna under test. It's a little hard to see from this image, but we can scan using this theta arm. This is the probe antenna that will go around and take a look at the horizontal or phi equals to 0 scan of the antenna. And then we can do the vertical phi equals 90 degrees scan of the antenna. So here's a better view, I would say. So here's the extender, and in this particular case, we're feeding the antenna under test through the package, and so the probe antenna once again is here, and it's taking a scan. In this particular case, 120 degrees. So in the waveguide feed measurement, in this particular case, we have two samples. And so the blue is representing the simulation, and then the red is representing the measurement. And so in some cases, we have reasonable agreement. This is, we know that there's some particular issues, and we're also seeing some of the, I would say, the patterns skewing as we get higher in frequency, around 210 gigahertz. We see some squinting that we didn't originally see in the original design of that antenna when we did simulation of the radiation patterns. Now when we do the probe feed, it gets even worse. So we have a lot of noise in the scanning, as you can see, and this is going from 180 to 210 gigahertz. The reason I think I shouldn't say that because I see we kept the frequencies the same, but we do have some bandwidth differences because of either probing or taking the measurement using the waveguide. With the waveguide feed, I think we had narrower bandwidth than with the probe feed, but where we should be expecting to see the peak at the center, in this particular case at 190, we're having a null. So, that's a problem in and of itself. And whether it's attributed to the radiation issue with the probe, I'm not quite sure. I didn't ask my student, but we definitely see that we have a problem here between the simulation and the measurement. So he says air to overmole mismatch, he believes is really what's causing this destructive reflection. Then we did some gain and efficiency measurements in order to see what things look like. And we looked at the frequency range from 180 to 200 gigahertz, and set the backside waveguide feed calculations, take into account the de-embedding, the loss of the package transition. And so that's really, once again, taking that measurement right here. So we've got some additional line length that we're trying to account for. And the measured peak gain range from 8 or 7 up to 10 dB, and the simulations in some cases agree, but at the higher frequencies there's some deviation. And then the difference between the measured and the simulated radiation efficiencies. So we really had some loss here at the 200 gigahertz range. And then we have another sort of efficiency measurement, and that's really now taking into consideration that waveguide feed from the backside. So some of the gains that we see here, where we're going from 7 to 10, now we're going from more like 3 to 6 on the measured side. And so that also speaks to the fact that we need to have designed a better transition. Okay, so the conclusion about the work is that the slot bow tie antenna it's a broadband antenna that we were able to design, and it gave us the opportunity to look at using the EQFN package as a host for it. And in the development of the antenna and the package, and then to be able to measure the performance, we found that the GSG probe did impact some of the radiation patterns, but also alignment of our probe to a holder was a problem. We had asymmetries due to our laser etching, which allowed us to be able to make a probe measurement. And then on the backside waveguide technique to feed it, we have some not the most optimized design of the transitions. And so we do get what we would call undisturbed radiation patterns. However, the transitions were somewhat complicated, and then our bandwidth, our 10 dB bandwidth was limited to only 18.4 gigahertz. And that's less than what the traditional antenna bandwidth would be if it were standalone. And so the slot bow tie vehicle, test vehicle for us, it mimics the layer by layer stack up found in the flip chip QFN package, and it does have potential for integration with other planar antennas. And we had also designed an E-shaped patch antenna, which used similar techniques. And we looked at that at WR8 and WR5, but I'm not sharing that work. But those antennas have less bandwidth, and then but they are smaller in size. So I think my last slide is just a list of references again.